Okay, welcome back. So in my last class, I did directional derivative. Okay, so I'll come back to that. I'll come back to that in a short while. But I want to do some unfinished business from the class before that, where I did chain rule. Okay, so I forgot to tell you about implicit differentiation. Okay, so once I get over this, after that I'll come back to directional derivatives. Okay, let me just finish this part. I'm sorry I forgot this implicit differentiation. So what is implicit differentiation? Suppose you have a function, say capital F. It is a function of two variables, x and y. And suppose your y is again a function of this independent variable x. So basically what we can do, we can write this as f of x, y of x. Okay, fine. So now if you have a relation of this type of f of xy equal to 0, okay, then now if I use chain rule here, see, if you recall, the chain rule was like if I have a function, I mean say f, which is a function of x and y, where x and y both were functions of a single variable t. So then, if I want to find out your df dt, so then this is going to give me del f del x dx dt plus del f del y dy dt. Okay. So likewise, so suppose I have this relation, and now what is happening? I mean, what I try to do, I try to find out the derivative of capital F with respect to x. Okay. Now look at this and simply compare. I mean, this one with that one. So obviously, this is going to be equal to 0, right? So this is going to imply, so del f del x dx dx. Okay. So here, I mean, the role of that variable t is taken by this variable x, because y itself is again a function of x. So then it is going to be del f del y, and then dy dt, this is equal to 0. So from here, you
Sir,
will find,
dx.
oh, this is x, sorry, this is x, yes. So from here, you will find out that if you have to find out dy dx, of course, I mean, if your del f del y is not equal to 0, if del f del y is not equal to 0, then I mean, you can find out the derivative of y with respect to x, and this is ordinary derivative by using this expression. Okay, and this is called implicit differentiation. This is called implicit differentiation. Say, suppose I take this exercise. Say you have a relationship given by something like this. Okay, so now you are told to find out your dy dx. You have to find out dy dx. So now, if I look at this expression, then I can write it as f xyj equal to x2 plus y2 minus 3xy. So I get an expression like x squared minus x, y squared minus x. Okay, so this takes care about your implicit differentiation. So now I want to get back to directional derivatives. Okay, fine. So this is simply something like leftover from my class earlier. Okay. Not yesterday, in a previous class, what we did directional derivative. Directional derivative, and let me just simply quickly do a recap. So what was that? I was a vector in the direction of a unit vector u cap in the domain of definition of this function. Okay. So if I want to find out the directional derivative of this function, right, in the direction of u cap, so then minus f of xy divided by x, where this unit vector u has components a and b. U has components a and b. Okay, and we also proved a theorem. That du this it is simply given by your fx xy into a plus fy xy into b. Okay, and this I could have shortly written as, I mean, fx fy dot this. Okay, fine. So now let me come to this vector. This is of course a vector. Okay. So this vector, I mean, it is called gradient of f. Okay, gradient of f. So, and it is denoted by this symbol, gradient of. This is the symbol for gradient of f, and this is simply your del f delta psi plus del f delta j. Okay. Now, similarly, I mean, this is for a function of two variables. Say, suppose we are considering a function of three variables. Say we are considering a function of three variables. I mean, f is a function of x, y, j. So then, this is simply what you will do. You will simply expand it to the third dimension. That's, you will expand it to the third dimension. This. Okay. So, for example, I'll just do an exercise. Say, and we will have enough examples in 3D also. Don't worry about this. For the time being, I'm going to do, say, f of x, y. Say, suppose this is x squared y cubed minus 4y. Okay. So, what you have to do, you have to find out the directional derivative of f at the point 2 minus 1 in the direction of this vector v equal to 2i plus 5j. 2i plus 5j. So remember, whenever we try to find out directional derivative, firstly what we have to do, whatever direction you have. So firstly, the first task you have to do is that you find a unit vector out of that given direction. Okay. So that is why firstly what we are going to do here, v is given as 2i plus 5j. So what I'm going to do, firstly I'm going to find out the unit vector along v, and that is simply going to be given by 2i plus 5j divided by what? 4 plus square root 29, right?
Yes.
Okay, fine. Thank you. So then, if you have to find out the directional derivative, so now I will find directional derivative of f at the point what 2 minus 1. Okay. So for that, firstly, what I will be needing. Simply what? 2x y cube comma then 3x squared y squared minus 4, right? Is it okay?
Yes, sir.
Fine. Fine. So grade of f at the point 2 minus 1. This is going to be 2 to the 4, and this is going to be minus 1. So this is going to be minus 4, and then 3 4 are 12, and this is 1. 12 minus 4, this is 8. Am I okay? Fine?
Yes.
Okay. So, sorry, this is V. This is V. So,
And that is minus 1. 2 minus 1.
2 minus 1. Yeah, thank you. 2 minus 1. So, this is equal to simply your grade at 2 minus 1 dot V cap. Okay. So, this is simply minus 4 8 dot. You have to just do this 2 by square root 29i comma 5 by square root 29. Sorry, why do I need I here? Because I'm using this. So ultimately this is going to be square root 29 minus 8 plus 40. So 32 by square root. That's okay. Fine. So so far so good. You think that this is pretty mechanical? Okay. But again, in physics and engineering, this directional derivative, for that matter, the gradient vector, it has a lot of importance. It is a very significant concept. Okay, so let me tell you why it is so significant. I'll just let me get back to let me get back to this one. Let me get back to just concentrate here. Just concentrate here. I would like to draw some conclusion from there. Okay, fine. So, what is this? What is this? We had a function. We were given a function of two variables, say x, y, right? So then, what we did, we found the gradient of the function at a particular point. I think it was 2 minus 1, right? At a particular point, 2 minus 1. Okay. So at different point, we are going to have different values of this gradient. And now you know that this gradient at a particular point, it is nothing but a vector, isn't it? It is nothing but a vector. For example, suppose I consider this say two-dimensional plane, and now they are not very well interested. I'm going to make it smaller. So 2, 4, 6, 8, 2, 4, 6. I have a purpose behind this one. 8. So this is 1. So this point is, this point is sorry, this point is your 2 minus 1, right? This point is 2 minus 1. So this is 2, 4, 6, 8. Okay. So now at this point, what we have found out, the factor is given by minus 4, 8. So the vector is going to be what? Minus 4. So this is your minus 2. So I'll have to go 4 units towards left. Okay, fine. And then 8 units up. So 8 units up, if it is 8, so this is going to be okay. So what is going to happen? Eventually, this is the vector. So this is the vector, your gradient f at 2 minus 1. Is it okay with you? Fine?
Yes, sir.
Right? So that means the function, from the function, we'll be able. Now, suppose you are given a function. Okay, at a particular point. So now, like say, if that function, it is going to represent, I mean, some variable different phenomena. So suppose something like temperature. So if you want to have an idea, the rate of change of temperature is going to be maximum. So then what you'll have to do? Gradient is nothing but what? Rate of change of some variable along a particular direction. Is it okay? Fine. Sorry, not gradient, sorry. Directional derivative. Directional derivative is nothing but the rate of change of a function in a particular direction. Isn't it? Is it okay? Fine. So if you want to find out, say suppose the function is 10. If you want to find out the, I mean, rate of change of temperature, in which direction it is, I mean, increasing fastest, right? So then we will have to take help of, this gradient vector. So how it is? So now let us come back to the definition of directional derivative in terms of gradient vector again. So suppose I am considering the directional derivative in the direction of u cap. So then you know that this is simply grade f dot u cap. Okay, fine. And of course, suppose I am considering either one, right? So then this is going to be nothing but what? Your grade f at x naught y naught, then u cap. Then if say here you have seen that grade f is nothing but a vector, right? And I'll be giving some vector like u cap, right? If suppose the angle between them is theta, so this is simply going to be cos theta. Is it okay?
Yes.
Fine. And you know that u is a unit vector. Right? So this is going to give you simply grade f at that point. In the direction of u cap is going to be maximum, right? So then I will be seeking the maximum value of this, isn't it? Right? And the maximum value is going to be obtained when theta is equal to Am I audible? Am I audible?
Sometimes the video is stopping.
Okay. Okay, fine. But I'm still audible, right?
No, sometimes you are not even audible.
Right now, am I audible?
Yeah.
Okay, fine. So again, let me come back to this question. See, I am trying to maximize this directional derivative, okay? And I have got this expression for directional derivative, right? So then you know that this is going to be maximum when your cos theta is 1, and that happens when theta equal to 0. Okay? Is it clear?
Yes.
That means
Yes.
if theta equal to 0 here, now look at it. What we must have, the direction of u cap and the must be the same. Is it okay? Fine. That means the directional derivative is maximum in the direction of the gradient vector. Is it okay? Fine. So you may be thinking, I mean, where it is going to be, useful. Let me consider an example, a practical example. Okay. Visualizing maximization of a function, you must visualize the gradient of a function at a point as a vector. So suppose I am considering a function t x y j. So this is nothing but t represents the temperature at a point, and it is in terms of Celsius. Okay, the unit is Celsius. And again x y j, it is nothing but the coordinates of a place. Okay, and if I consider x y j, the units of x y z, they are in meters. Okay, so suppose t x y j, it is simply given by 18 by 1 plus x squared plus 2y squared plus 3j squared. Okay, so then the question is, in which direction temperature increases fastest? Temperature increases fastest at 1 minus 2. And the next question is, what is the maximum rate of increase? What is the maximum rate of increase? Okay, so these are the two questions. So you can see that this is a very practical example here. Of course, I have taken it from steroid book, and now, firstly, you know that the directional derivative. Is maximum in the direction of the gradient vector. So, if I want to find out in which direction rate of change of temperature is fastest, so what we must do, firstly, we have to find out the gradient of T. Okay, and gradient of T. This is going to be minus. Firstly, this to the power minus 1. I can think about, right? So then it is going to be minus then 80. I'll rewrite it. Please don't. So this is going to be 3. Isn't it? Right? So what I will do, and similarly, the second component, instead of 2x, you are going to have your 4y. Third component, you are going to have 6z. Okay? So that is why I can write this as your grade T. This is minus 160x 3j squared. Then I will have 4y coming, so minus 320 by again 320y by again the same thing, and here it is going to be 6z, so 6 into 8, so it is 480 j, and the same thing. Okay, fine. So now, if you want to find it, at the point 1, 1 minus 2. So let me check what is the denominator for 1, 1 minus 2. So denominator is 1 plus 1, 2. Then this is going to be again 2, 4, and then 3 into 4, 12. 4 plus 12, that is 16. Yeah.
Will there be a square in the denominator?
Yeah. So it is, yes, it is. Thank you. Yes, I forgot that. Okay. So this is going to be minus 160 into 1 into 16 squared minus 320 into 1 into 16 squared and minus 480 into minus 2, right? Minus 2 into 16 squared. Okay. So what you do, I mean, you simply find out this gradient. You simply find out this gradient at this point. So this is going to give you some value what it is going to be. So it is going to be 10 minus 10 by 16 minus 5 by 8. Okay. So it is going to be minus 20 by 16 minus 10 by 8. Should I keep it like this? And this is going to be what? 16 threes are 30. I think it is going to be minus. It is going to be 30 by 8, something like this. Okay. So I mean, eventually, what you do, you simply simplify it. Okay. So once you simplify it, you know that the what in this direction, the rate of temperature, change of temperature is going to be the maximum, fastest. Okay. And what is the maximum rate of increase? What you have to do? You have to simply find out. You have to simply find out mod of grade T. That's it. Mod of grade T. Okay, because you know that. I mean, like say the maximum value, like from the grade formula, the directional derivative. Directional derivative is nothing but the rate of change of that variable in that direction, right? And this is given by this, and we have seen that it is fastest in the direction of the gradient vector. So that means when the angle between these two vectors is 0, and again since the value of this is equal to 1, so eventually the directional derivative is going to have this. So eventually, if you take the mod of this, absolute value of this, or the length of this gradient vector, so it is going to give you the maximum rate of increase. Okay, please try it at home. And the maximum rate of increase is going to be, I mean, Celsius per meter. Remember that. Okay, fine. So and again, I will show you the slides quickly. I'll show you the slides quickly. But before that, again, let me tell you about another application, because later on in numerical analysis and whenever in your future engineering studies, you are going to come across something like method of your steepest descent. Okay, method of steepest descent, and it is exactly opposite to method of steepest ascent. Okay, so ascent means when you are trying to climb a mountain. Okay, so suppose I am considering a mountain. I am considering a mountain, right? And again, you know that mountain can be considered as a surface, right? So that means I can consider it as a function of what? Two variables, isn't it? This surface I can consider to be the graph of a function. Is it okay? Fine. So
Yes.
So thank you. So now say suppose you are at the base of the mountain. So definitely you are going to have some coordinates of that particular point. So in x, y, z plane, this is x naught, y naught, j, right? So then, if you want to climb the mountain and you want to reach the highest point, so from here, if you want to start, then here if you take the gradient vector, it is going to give you what? And this is j equal to f of xy. This is nothing but the altitude function, isn't it? Right? It is giving you the altitude, the height at a particular point, isn't it? So then, gradient vector here at that point, it is going to give you the direction locally where the rate of change of height is maximum. So you move along that direction. After a while, you reach this point. At this point, again, you find out the gradient vector. So in this way, it is going to give you a path. And if you follow this path, you are going to reach the top fastest. This is what it is. Is it okay? Fine. And this has been described in your book also, but I don't know whether you understand it clearly. But anyway, don't worry about it. Let us just browse through this. And once you repeat my video, I think it is going to be more clear to you. Okay? So I will quickly browse through my slides. So this is the definition of gradient. So this is the theorem. This is the theorem that we had for directional derivative. And so we can write it in this way. I have already done this. And then the directional derivative, like say if you consider it in 3D, like say for a function of 3 variables, then you can write it like this. This is the definition. This is simply, the simple extension of the definition of directional derivative in 2 dimensions. And similarly, if you want to extend it to, n-dimensional vector, so then you can write it like this. Okay, so while defining limit and continuity, I have already explained these terms. Okay, so then there are, for gradient there are certain properties. You can easily prove them at home, and there will be enough problem in tutorial sheets. Okay, this we have already done, and this is just an information I have given to you. Like say for a function of 2 variables, if you want to check differentiability, then you can check it with the help of this condition. Okay, so if this becomes 0, then this function will differentiate at this point. Okay, fine. The point has been given in terms of its position vector. Okay, and this is about maximizing the directional derivative. I have already told you how it happens. Okay, so this is the theorem that it occurs when u has the same direction as the gradient vector of the function f. Okay. Now I come to a very important concept. So this is going to be very, very important. Tangent lines to level surface. Okay, tangent line to level surface. And this is where the gradient vector is going to come in handy. Tangent and levels. So what it is? See, for the time being, whatever we have done in directional derivatives, so what we did, we considered a surface as the graph of a function of two variables. Okay. Now, instead of that, let us consider a surface as the level surface of a function of three variables. Okay, it is given by these expressions. A surface. Okay, and now suppose I am drawing it here. Although the surface will expand more, I mean, please don't think that it is only the first octet. So this is the surface. This is the surface given by. This is the surface given by this level surface. Okay, function of three variables by j. Okay. Now, what we are doing? Firstly, we are going to consider a fixed point. Say p. Say x naught, y naught, z naught. X naught, y naught, j. Okay. And then what I will do? I will consider an arbitrary curve through this point p. Arbitrary curve through this point. For the time being, it is okay, right? So now this curve, which I'm calling it C, of course, I can have parametric representation of this curve, right? If C, I mean, it is given by this parametric representation. Say this parametric representation, and if this parametric representation means I am considering this for some parameter t in some interval, say, am I using a b here? So something like this. Okay. So now suppose the point p x naught, y naught, z naught, this they correspond to simply the point t naught in this interval. Is it okay? Fine. So that means what I can do, if this is the origin, so the point P or the vector OP, I mean I can define it through the vector R at T naught. Is it okay? Fine. So basically, I mean C is parameterized by this vector. This, right? So therefore the vector OP yes.
I was unable to hear you.
Okay. I think it's fine. The first part was it audible?
Yeah.
Was I audible?
Now it is okay.
Okay, fine. So now let us come back to, at least I am visible, right? So now for all points x, y, z lying in the curve C, if I consider this surface, so at all points lying on the curve C, I mean it will be satisfied by this equation. Okay, this part did you hear?
Yes.
Okay, so now if I want to find out the ordinary, so eventually now C f becomes a function of this interderivative t along the curve C, right? So if we want to find out the ordinary derivative of f, okay, ordinary derivative of f with respect to t, so then I can use chain rule, right? So it is going to be like this. This is equal to 0, right? Or dt, dy dt, dz, dt. Okay, and this is going to be valid for each point on the curve C. Okay. Now suppose I consider, so see, this is simply what? This is simply grade f, right? This is simply grade f, and this is simply r prime t, isn't it? So now, if I consider the value of the, I mean, gradient vector at the point x naught, y naught, z naught, so then what is going to happen? From here, I can simply write it as your grade f at the point x naught, y naught, z naught dot your r prime at the point t naught equal to 0. Is it okay? Fine?
Yes.
Okay. So now this has a lot of significance. So what does it tell you? This tells you that this grade f at the point x naught, y naught, z naught, it is perpendicular to r prime t naught. But r prime t naught is nothing but what? The tangent vector at the point x naught, y naught, z naught to the curve C. Is it clear?
Yes.
Right? Okay. So that means the gradient vector to the curve, at the point P, right, must be perpendicular to what? Must be perpendicular to the tangent vector. Okay. So now C was an arbitrary curve. So now if I draw, I mean infinite number of curves through the point C, through the point P, right? So then eventually I will get the complete surface, isn't it? Right?
Yes.
By considering infinite number of curves through the same point P, right? I can get the complete surface, or at least I can get a surface in the neighborhood of this point P, right? Okay. So that means the gradient vector is going to be normal. Gradient vector is going to be perpendicular to all the tangent line to those curves, right? So going to lie on the tangent line to the surface at the point P, right? So that means the gradient vector at that point must be normal to the tangent plane drawn at that point to the surface given by the level surface. Is it clear?
Yes.
Right? So that is the significance of gradient vectors. That is it allows me. So now, in our earlier, discussions of your vector calculus, we what we did, we developed the equation of the tangent plane at a point to a surface, right? So suppose that point is x naught, y naught, z naught. So then, if you know the components of the normal to the tangent plane at that point, so then my tangent plane, equation of the tangent plane was given by this. Okay. Now I have found out that. The gradient vector is nothing but these components A, B, C must be given by your fx at x naught, y naught, z naught, then fy at x naught, y naught, z naught, and fz at x naught, y naught, z naught. So this must be the equation of the tangent plane to the surface at that. Is it okay? Fine. And then if I want to find out the symmetric equation of the normal line, so that is simply x minus x naught by fx, because these are nothing but the direction ratios, y minus y naught by fy x naught, y naught, z naught, and 0 minus z naught. So fz x naught, y naught, z naught. So this is the equation of the tangent plane to the surface f of x, y, z equal to k at the point x naught, y naught, z naught, and this is the symmetric equation of the normal. Okay, so we can like very small example we can take. See, the question is find the equation of the tangent plane and the normal line to this surface. At -2, 1, -3. Okay. Can you recognize? This surface is going to be what? The shape of this surface. This is ellipsoid. Yes, this is an ellipsoid. So, and it is very straightforward. Obviously, what we can do, we can from this equation, I can simply write it as f of x, y, z equal to here k is 3. It is on this form, right? So your grade f, this is going to be what? X by 2, 2y, and 2z by 9. Okay, so your grade f at -213, you find it out. This is going to be what? -1, 2, -3, so it's going to be -2 by 3, right? -2 by 3. Okay, so then I'll quickly write equation of tangent. Equation of
Sir, it should
tangent.
be -3. Nabla F.
Just a minute.
Left. No, that is okay.
That is minus. That is minus. Yeah. So the equation of the tangent is tangent at this point. It is simply -1 into x plus 2 into y minus 1 minus 2 by 3 into j plus 3 equal to 0. Okay, you just simplify it, whatever you get. And your equation of normal, the symmetric equation of normal is going to be simply this x plus 2 by -1 equal to y minus 1 by 2 equal to j plus 3 divided by 2 by 3. Okay, fine. So in my next class, see in my slides I have again described the significance of the gradient vector. I don't want to repeat it. The slides will be available to you. Don't need to worry about it. In my next class, I'm going to do your maximum and minimum. Maximum and minimum, then absolute value, all those stuff. Sorry, absolute maxima, local maxima, absolute maxima, absolute minima, local minima. So what I would like you to do, so before my next class, I want you to go through a beautiful chapter in Stewart book. It is called How Derivative Affects the Shape of a Curve. How derivatives affect the shape of a curve. Okay. So if possible, I'll try to upload that particular chapter separately in my website so that you can have a look at that. But please go through that, because in order to prove the theorem for the conditions for the existence of maximum and minimum, so I'll be requiring some of the concepts from that chapter. It's a beautiful chapter. Please go through it. How derivatives affects the shape of a curve. Okay. So with that note, I'm going to end today's class. So then I'll see you in the next class.